Alright, hell yeah. So I've been in a rut, and this video, or a video like this, you just don't see on the internet. What we're going to do is we're going to walk our way through a textbook. I've been learning, by myself, and I just don't think a lot of people do that. So this is material mechanics. Now, for disclosure, I have taken this course in college, so I'm pretty versed in it. But still, I think I know how to use an equation to solve a problem. But what we're going to go, and most textbooks go through, is the derivations, which, I don't know, given enough time to pass, you go re-look at this stuff, and you don't even know what terms they're using. You know what I mean? Like, look at that. Well, what is that, a phi? And then, what else do we have? So that's what we're going to go through. So anyway, and hell yeah, so we're going to do torsions of circular bars. And I think the first thing to do is just read, and just to let you know though, but once we get into the equations, your mind's going to go blank, and you're going to be like, you have to kind of figure out what they're doing. So it is a good skill. All right, let's get into it. So it says in the first couple chapters, they discussed the behavior of the simplest types of structural members. So straight bars with axial loads. And this is what I'm doing. I'm kind of reading, and then I'm kind of intuiting what they're going to say. So I think that's a good challenge when reading a textbook. And then the other thing is sometimes you just get to equations where you're just like, nah, I think I might just have to kind of just brush through this and move on. But at least brush through it once, and hopefully when you come back, you'll pick up some more. Okay, so it says, now we consider more complex types of behavior known as torsion. Torsion is twisting of a straight bar, and it's loaded by moments. To twist something, you have to put a moment on it, or a torque. That's what this T implies. And I think even just right there to stop is like, anytime that you see this symbol for a torque, or if this was the letter M, that would be a moment, I would literally, in your mind or on paper, turn it into two forces, because that is the definition of a moment. A moment is just a couple. So if you have this symbol where you're applying a torque at a location, which is the center of this arc, and that's going to be axially right here, what you could do is just pretend like I always think like I do some welding. So I'm just going to weld a steel bar right there, lightweight steel bar right there, and then, basically what I'm doing is making, what are those called? Loss of words, but how do you, like a jack for a car? That's not a jack, but anyway, whatever takes off the lug nuts of a car. So I can, to generate this torque, I can weld those two little ends, and then pull down on that end, and then pull up on that end. And that would be two equal and opposite forces, and you're going to generate a moment. Cool. All right, so hell yeah. And when we do that, let's say this screw is already in this wood, and we need to actually get it in more. You know what I mean? We tried to do it we got this screw into this wood as far as we thought we could, but we're going to try to give it all of our juice to try to seal the deal. So when we go to this screwdriver and we apply a moment, well, maybe we don't notice the screws actually going in. So that's where this chapter tells us about what happens to this screwdriver when that happens. Because because the first two chapters, and what you should glean from material mechanics, is everything is a spring. If you have a chunk of metal, and then you pull on it axially, it behaves as a spring for its kind of usefulness. If we say, hey, this chunk of metal, we're going to get some strength out of it, I'm going to pull on it, and you know what I mean? I'm going to give it a working load, and it basically acts as a spring. The bummer is it's just really difficult to actually see the change in lengths of things like steel when we pull on them or push on them. But they are changing in length. And in material mechanics, you measure failure. There's a term called stress and there's a term called strain, and both are both kind of represent the same thing that's going on. Let's say you have a steel bar. I always do this. This is kind of just material mechanics 101. If I have a steel bar and I pull on it, at some point it's going to be maybe like unusable. I always like, even though steel totally stretches out and deforms, and then necks down and then stretches. What I like to visualize is that materials, like even a steel bar, is made up of, very much like covalent bonds, where they're going to stretch. You can get force on that steel, and then at a certain point it's just going to break. And even though with steel, like what's going to happen is you're going to get to that, what I would call quote unquote breaking strength, and then it's just going to stretch out. And in some applications, if that stretches out, maybe two other members could take the load, and it's actually no big deal for that thing to stretch out. Or if this is like supporting something in a hanging environment and it starts to stretch because you got past that so much weight, well, then you're just screwed. You know what I mean? It's actually, you're going to get to a point where you're not, well, I shouldn't say that, because even with steel, as it actually stretches out, you're almost cold forging it, where you pack in this is where I get caught up. Every time I go into material mechanics, I feel like I need like a little material mechanics 101, and I don't have my writing utensil on the screen. That's totally fine. Anyway, I just wanted to make a video, and hopefully we don't strike out on this. But hell yeah, as you pull on steel, the iron molecules, which are just kind of swimming, I mean, I shouldn't say they're swimming, but they're the electrons that kind of, oh damn it, this is awful. But anyway, you have like a sea of electrons. Oh, this is so bad. But when you pull on steel, and you actually get, voids get filled with more of those steel atoms, and you get a stronger material. So there you go. That's the simplest. As you pull, and when metal gets ductile, and that's kind of what they call the yield. That's when it's starting to yield. It actually becomes stronger, even though it's necking down. Even, you know what I mean? Poisson's ratio says when you pull on something lengthwise, the volume is going to decrease, and so that means that the stress is going to increase. But anyway, that's why I don't like to. I just don't think like people have a general good understanding of stress. So I try to teach material mechanics from not even having to use the word stress. But hell yeah. So you have a chunk of steel. You give it a rating. You say, hey, you can pull it this much until it starts to stretch. If it does start to stretch, yeah, actually it gets a little bit stronger. It'll take more strength to actually stretch it during its and what do they call that? Well, there's two different at the yield point, you do get perfect plasticity, where it's just like the second it starts to stretch, it's going to take the same amount to just keep stretching it. But then you get those molecules to rearrange, and that's called hardening. And so you do get strength, what do they call it? Strength hardening. You know what I mean? A ski edge, when it hits hard ice or rocks, we'll get, what do they call that? But anyway, it's hardening of the steel. And so yeah, I would assume that's a very, cold forged technique, where you're just, You know what I mean? You're not like melting the steel, but you're applying force and making stronger bonds. All right, holy hell. So that's how complicated steel is. But if you just think that, hey, right at yielding, like that's when your life's going to rapidly change as an engineer, because the bridge you built broke and a lot of people died. And it's probably at that yield that, you know what I mean, crap started happening in the structure that you designed. So from just a very practical and simplistic model, I consider yield strengths to be, you know, kind of like the ultimate strength, because all material has a linear range anyway. And if you're working in that linear range, you get plenty of strength in that linear range. You hardly get too much extra strength, and the extra strength that you are getting has to come with deformation of, you know what I mean? If a material is being stretched in the linear range, you also have this very magical property that when you stretch that bar and then let go, all the molecules go back to the original location. And so that's very fascinating. All right, hell yeah. So that is pulling on a chunk of steel. The molecules act as springs. If you have a chunk of steel and you don't pull on it, it's a certain length. You pull like 1 pound. It actually lengthens. You know what I mean? And measurable. You know, depends on asterisk on that. You know what I mean? Whatever devices could measure very small changes in length. You know what I mean? You get 2 people to push on either side of a tank. That tank is changing in length. You know, you just need a very sensitive device to show that. You get 4 people, 2 on each side now, pushing on a tank. Its length is going to, you know what I mean? With the 2 people on both sides of a tank, let's say its length changed 5. 5, like whatever, you know, throw a tiny unit on that. But anyway, and then you get 4 people pushing on 2 on each side of that tank. Well, it's going to change in length by 10. It's going to shorten by a quantity of 10. So, and that's cool because springs are like that. They're linear. If you pull 1 pound on a spring, maybe it's going to lengthen an inch. Pull 20 pounds, that spring will lengthen 2 inches. All right, hell yeah. Now, when it comes to twisting stuff, that's where it's just like, well, I understood pulling. You know what I mean? Because it acts very much like a spring. Even pushing. If I push on a concrete pier, hey, it's actually going to act as a spring the same way. Take that load off, and it's going to rebound. And as long as you're in that linear elastic range, the materials will pop back to their original location. This is kind of a property of... Yeah, a property of solids. So that's cool. All right, holy hell. Let's move on. So yeah, so that's the simplistic, and now we're getting into torques, and they're loaded by moments that tend to produce rotation about the longitudinal axis. So I guess they produce. So torques produce rotations. We're probably going to be doing problems where, you know, I mean, hey, this screw is stuck and it's not moving, but we're applying a torque. Well, guess what? We have to have something to resist that torque. If we're applying a torque and it's not moving, you know, this thing should be rotating. If it's not, there's an equal and opposite torque on the other side. So if this is going this way, this screw is providing an equal torque in the other direction. And anywhere along a little slice of this, the material also has to withstand that torque on either side of that slice. So that's what we're going to be taking a look at. Okay, hell yeah. So for instance, when you turn a screwdriver, your hand applies a torque T to the handle and twists the shank of the screwdriver. Other examples of bars in torsion are drive shafts in automobiles, axles, propeller shafts, steering rods, and drill bits. So these are all bars in torsion. So in an ideal case of torsion, loading is pictured in this next figure. So this is going to be ideal. Rigid and fixed. Oh, and check it out. They even put these little welded metal tabs, you know what I mean, to show that those are the torques being applied. Very visual. Where these arrows are not, you know what I mean, it's not super obvious. Okay, hell yeah. So that was the figure on the next page, and that's figure 532. I can't even read. So this is figure 328. And that shows a straight bar supported at one end, fixed, and loaded by two pairs of equal and opposite forces. The first pair consists of the force P1, and this is where you want, like, you know what I mean? Hey, it said two pairs of equal and opposite forces. These are the pairs of equal and opposite forces, and guess what? We have two of those, you know, pairs. This is the first pair, P1, P2, and an equal distance D1, and this is the other pair of equal and opposite forces. These are equal. P2 is equal to P2, and they're opposite. This one's up, this one's down. Equal distance D2. And this one provides that moment in this, if we're looking at the bar this way, it's going to be counterclockwise, and this provides a clockwise moment or torque, T1. And if we do the, you know what I mean, if we take this as our origin and we say, hey, what's the moments, the sum of the moments about this point? Well, we're going to go up to this P1, a distance of, if we're calling this distance D1, and I'm starting here, we're going to go half of this, so D1 divided by 2 times P1, that's the torque in this direction. And if I'm looking here, I'm going to be right-hand rule, my thumb's going to be into the page, and so it's going to be a, we'll just call that a positive. If it's into the page, is it positive? Nah, that would be negative. So if my thumb's into the page, this one's going to be a negative torque that direction. That's going to be a clockwise torque. So yeah, that's negative. And then if I go from this point down to here, and what's the value on that? Half of this distance times P1. Now over here, I'm going to go half the distance, half this D1. So D1 divided by 2. I'm going to go from there to there, multiplied by this force. And that right-hand rule, my thumb is going to be into, you know, that direction. And that'll also be clockwise. So that'll be negative. So I'll have this negative torque, P1 times D1 divided by 2, added to this, P1 times D1 divided by 2. And if I add those two halves up, then we get P1 D1. Because we had P1 D1 divided by 2 plus P1 D1 divided by 2. That adds up to P1 D1. So, and I swear it took me a while, you know what I mean, because this is something where if you have a moment, this is the definition of a couple, where you have an equal and opposite forces, a particular distance away from the center of something, then the torque generated by that couple, you know what I mean, the value of that couple is just one of the forces times this distance. And so I think people just go from memory on that one, but it's this one, if you don't know where it comes from, other than the fact that, oh, if I have a couple, it's just this force times that distance. You know, set it up. Sum the moments from right here in the middle, and then see that it's half the distance P1. And you can sum the moments anywhere. You could sum them, and that's the wild thing about summing moments. I could come in outer space right here and sum the moments, but let's just sum the moments right here. If I sum the moments right here, P1 goes through where I'm summing the moments. So this generates no torque. This generates a torque, and it's a distance of D1, and the force is P1. So if I'm summing the moments about here, I get that negative P1 D1. And if they're calling this positive, well, they're just using absolute values, because this torque is generated that way, and then this is generated that way. So T1 and T2 are opposite. So if we're like, one should have a negative sign, in this, and that's the other thing with textbooks. You know what I mean? You're like, what are they trying to tell me? They have not chosen a direction. They're just saying the magnitude of T2 is equal to this. And I would probably throw some absolute value signs on that. I don't know. That would just be very helpful, because obviously they're not showing you that these are opposite, even though they're doing it visually with arrows. That torque is going that way, this torque is going that way. Which using these double arrows shows that, hey, this is the axis of a torque, which is a force times a distance. And so this symbol is more visually representative of what that couple torque or moment is doing. It's trying to spin this rigid bar. All right, booyah. Okay, hell yeah. So I've got some coffee, so we're gonna take a sip. And hell yeah, we got ice water. And, you know what I mean, maybe this is just an intro to torsion, but just even reading the introduction, because sometimes these chapters, like the whole introduction, well, it's just going down to here, kind of spells out everything that we'll be doing. So it is kind of an important chapter to kind of slow down on. So hell yeah, so we've identified that we have the pairs of forces. The first pair consists of the forces P1 acting near the midpoint of the bar. And even just right here, the fact that we went down to this figure, kind of studied it, then going back to reading about what they're talking about. So now when it says the first pair consists of the forces P1, I can even just visualize that picture in my head now. And it says P1 acting near the midpoint of the bar, and then the second pair consists of the forces P2 kind of acting closer to the end, maybe 3/4. So at the end. So each pairs of forces forms a couple. We talked about what a couple was, equal and opposite, and equal distance away from a center point, that tend to twist the bar about its longitudinal axis. As we know from statics, the moment of a couple, so that's we sum forces and we sum moments. So a couple is two forces separated by a distance. So that's the take-home point. Anytime that you see this T, and I'm just so glad they're doing this, because this is how I would have set up this introduction. You know what I mean? If you're showing a torque, show that it's just two forces separated by a distance. Hell yeah. Which, like, if I just have these two on this bar, you know what I mean? Hey, I have forces are balanced in this direction. This one's going this way, this one's going this way. They're balanced in this direction. But because we have a moment generated with this, we have to balance that moment. So that's kind of the from statics. Some of the forces in any particular direction have to be zero. And also, if we have a torque generated, that means that this thing is just going to spin in space. If it's not fixed over here and we apply this torque, one, it's going to, and let's say it's stationary, we start to apply this torque. That's also, from the dynamics perspective, it's like make a story out of it. Hey, this chunk of bar is floating in outer space. At some point, I start to apply this torque. Well, guess what? It's going to spin. And that means that it went from not moving to now spinning. And so because we're applying this force typically involves a change in velocity. So this thing had zero velocity, and now we're applying forces. Now we're changing the velocity, and as long as we're applying this force, it's going to speed up and speed up. Same thing with two forces separated by a distance that are equal and opposite. We're going to have a change in velocity, and what's going to change the velocity? What's going to change in velocity is the spin. It's going to go from stationary to starting to spin around this axis. And that spin is going to increase and increase and increase. And all of this, even though spinning is kind of complex, still, this bar is made out of atoms. It's made out of little chunks of mass. If we apply a force, let's say this is where, for next time I'll definitely get my arrows and be able to draw. But if I have a chunk of mass here and that's just floating in outer space and I apply a force on it, then it's going to move in that direction. Let's say I have a chunk of mass, and I think a cool picture is just like hook up a very lightweight tube, and then have a fuel source right here, and then have a small little cone, and then so you could light this fuel, and that's just going to be a chunk of mass with a rocket, like a massless rocket strapped to a chunk of mass. And then we're going to light that rocket. That rocket is going to apply a force. And the cool thing about a rocket is it's literally applying the force by taking mass and colliding it. Was that what you would say? Because the mass is getting thrown that way. And the only way for that mass to be stationary, so you have the fuel goes in. Oh yeah, that's fascinating. The fuel before ignition is like right next to the bigger mass. So you have one little droplet of fuel, you have a bigger mass, and that at the instant of ignition, that little tiny chunk of droplet of fuel ignites and goes that direction. And sure, you do have a little cone. Like you could consider it even like a rifle. You know what I mean? So like, and as it's going from here to there, and then finally leaves the exit of the nozzle of the rocket, or like a rifle going through a rifling and exits, it's going to have some sort of velocity. So you have a very small little droplet of mass. It has zero velocity, and then it changes velocity, and then leaves. The second it leaves, it's no longer doing anything. It is going to travel that velocity forever in the universe. But it went from 0 to that velocity, down that rifling, or through that rocket cone. And in that process, the only way for it to do that is that how that works? Is to push off on something. Yes, because even though a rocket isn't, it's not super obvious that it's like a gun with rifling. That's why actually showing a rocket with like a rifle, because you have an explosion, but all that explosion is getting directed. Because if you just have this little droplet in outer space and then ignite it, let's say it's made of a bunch of molecules. Like, hey, the explosion is going to go in all directions. And the center of mass isn't going to change. But what you have is that you took that droplet, exploded it, and you have controlled the explosion to just go one direction. So you've taken all that energy that was supposed to go in all directions, and you funneled it down rifling, and made it go that direction and then leave. The only way for it to go that direction is to... see, that's where I'm kind of getting bummed out. But yeah, it applies an equal and opposite force. I'm just going to leave it at that. I think we got to a pretty good point on that. Hell yeah. And then it starts to move. But anyway, so just back to Newton's is very, like, I always go back to this. Just like, especially in imagining chunks of mass in outer space and then applying a force. But what the hell is a force? You know what I mean? Like, there's very few things that you can apply forces that don't involve some sort of mass. You know what I mean? Like, that's why, like, the rocket's a pretty good example. You're taking a chunk of mass and having it go that way, changing its velocity, and it's just a tiny little chunk of mass that's going to push back on this bigger chunk, and that's going to start to move. And there's a couple ways to look at that. You can take that tiny little droplet, place it up against the bigger chunk of mass, and you can say, hey, the center of mass is right. It's not quite in the center of the block, you know what I mean, that we're trying to move. but it's just a little bit closer to that little droplet. Well, guess what? When that droplet flies across the universe this way, it applied the force on this bigger mass. The center of mass always stays right there. So as this little droplet is going that way, this chunk of mass is also moving that way. But the second that little droplet goes through the rifling of the rocket, both have met their final velocity. So that droplet, that gas, or those molecules that got ignited are moving this way at a certain velocity. This chunk of mass is now moving this way at a particular velocity, much slower. But hell yeah. Okay, so and the second that droplet leaves the rocket, now there is no more force. The only force on that chunk of mass was during that change in velocity. So that's kind of interesting. But that's just for one droplet. That's why I came up with the scenario of you just have this chunk of mass, of lightweight tube, a carbon cone, and we're constantly feeding. We have just a big old feeder of fuel, and we ignite that, and then we're lighting it, and now we can visibly see this mass move because a ton of droplets are exploding, and that's applying a force. And I guess the take home is that when you're applying a force on a mass, you don't just get a constant velocity, you know what I mean? You get a change in velocity. It had zero velocity and now it has some velocity, but it's keeping doing that. You apply a force for 1 second, cool, you get a change in velocity from 0 to a particular number in 1 second. If you keep applying that force for the next second, cool, we're going to get another change in velocity. And as you keep applying that force, we're keeping changing our velocity. So that's kind of the take home. And the same thing with rotating things. If I apply a torque and this thing's just floating in outer space, it's not only going to start to spin, it's going to spin faster and faster and faster until I stop applying this force, or there's an equal torque due to maybe resistance, or just applying a torque to counteract that would stop the increasing, change, going from spinning to increased spinning speed. Which spinning speed, what the hell do we call that? Angular acceleration. If something is just spinning, you know what I mean, like whoom, whoom, that's angular velocity. If something is speeding up, starting to spin faster and faster, that's angular acceleration. And you can have angular deceleration is just angular acceleration with a negative sign. All right, hell yeah. Booyah, more coffee. All right, hell yeah. So I think we need to go back to where we were. We didn't get very far. We were talking about the moment of a couple is equal to the product of one of the forces and the perpendicular distance. But you know what I mean? Don't memorize it like that. That's crazy. You know what I mean? Unless you've done it so many times. But if you ever forget, that's where it's just like when I learn stuff, it's just like, I don't like that. Just know that they skipped a step. You know what I mean? They didn't take this from a fundamental. They say, hey, this is a formula. Let's use it. If I have a couple, hey, the moment generated by a couple is one of the forces times the distance between those two forces. That sucks because it's not a fundamental. And all you have to do is just being like, well, take the moment right there. Well, yeah, no duh, it's this force and that distance. So you could take and I spent about a year or two just taking the moment always in the middle. Hey, half the distance times this force plus half the distance times this force, and both of those are in the same moment direction. They're not canceling, they're additive. But, you know, I mean, that's the secret sauce, is just like, whoa, I can take moments anywhere, which is wild. That's going to be for another video. Sometimes just like we're kind of welding a little chunk of steel, the other thing I like to do is like, hey, let's glue a chunk of foam to this. So I'm going to have a chunk of foam here and a chunk of foam all the way up here. Now that chunk of foam is part of this rigid body. Just a rigid body just means like, hey, that chunk of foam moves with the body. If I start to rotate it, that chunk of foam starts to rotate that way. That's all the definition of a rigid body is. That's also something with textbooks, to always go back to like that first page of the first chapter in the book, because they actually talk about stuff that you just totally, you're just like, oh, I never even, I know they're using the term rigid body, but I don't know what the hell they're even talking about. You know what I mean? What's the definition of that? But then I can have this chunk of foam up here, and then I can take the moment on that chunk of foam. And that kind of makes sense because I'm taking a moment on the rigid body. I have this force here that is a shorter distance, so it's not generating too much leverage. But it's from this point, this force would be causing a torque about this point this way. But this torque, this force is a little bit farther away, and it's going to be causing a moment about this. And the distances kind of cancel. And then so what we're left with is just the same thing. You know what I mean? If I take the sum of the moments of both of these forces and the distance to this point, you know, on a glued chunk of foam that I glued to this rod, I would get the same P1 D1. That's going to be the sum of the moments. And we have a net moment. You know what I mean? So if this bar is just floating in outer space and we have these forces as this couple, we should expect spin. Cool. But we already know, like over here, this thing's rigid. And even if I did have this moment, well, probably this would counteract, and this is attached to something. All right, hell yeah. Okay, so yeah, we're just going to get through this introduction, and that's it. But hell yeah, we at least started our computer and made a video. You know what I mean? I think I kind of ran into a brick wall of making the math videos with the calculator and the overhead camera. I don't know. You know what I mean? I'm just at the point where it's just like, well, other people have made videos, so like, where should I spend my time? I have no idea. But I still need to make videos just to figure out how to get better, and I think that's a very valuable, you know, thing that I always look forward to. It's just like, hell yeah, just slowly start to improve. But yeah. All right, where the hell are we? So yeah, talking about that moment of the couple. Yeah, again, they're just going to pop out this formula. It's the product of one of the forces and the perpendicular distance between the lines of actions of the forces. All right, I can dig that because this P1, I could have instead of just a little nubbin of steel, I could have a little nubbin, and then over here, a little L-shaped. And I'm going to take this P1 and I'm going to pull on that little L shape right there. Well, now what? It doesn't seem like the loads, this would be pulled from that point, and then if I pulled P1 from way over here, hey, is that going to change anything? No, because the line of action of the forces, that's what we're looking at. And if we have equal and opposite forces, they are, for this couple to be a couple, they cannot be in line. They have to have some sort of distance separated between them, and it's the shortest distance between those two. So I could have any two lines in space, and I'm saying that those lines have to be one. I guess they don't even have to be parallel, because you know what I mean? Let's say this is up at a 45. Well, let's not get into that. Because, I mean, you would have to have, if this was up at a 45, you'd have an upward force. Something would have to apply a force down for it to be like in, you know, equilibrium and stuff. But hell yeah. So parallel forces, shortest distance between them, perpendicular, kind of the definition of the moment generated by a couple. And that's kind of interesting that the couple is the thing. is the two forces separated by the distance. The moment is the value of that. You know what I mean? And then moment also is just moment of a force. That needs to be talked about. Like, because you have a moment of inertia. What the hell is that? Well, that's you have some sort of mass out here, some sort of distance away. Let's say, yeah, and then like a string and a mass out here. So you have some sort of mass, it's a distance away. But guess what? Moment of inertia is second moment of mass. We're going to take that distance and then multiply by that distance again. So that's going to be this distance squared times that mass. Where a first moment is just, hey, this mass times this distance. So first moment of inertia, probably not a very useful term. Doesn't like I've not come across it, but the second moment of inertia, where you have, am I even getting this right? Yeah, or it's just mass. Sorry, not mass moment of inertia. Yeah, they call it mass moment of inertia. It's mass and a distance. So it's first moment. Yeah, this the second moment of mass. There you go. And that's called the mass moment of inertia. Inertia just meaning that, hey, if you're going to start moving that mass about, this point over here, well, hell yeah, it's I think that's kind of what they're getting at. But yeah, that's a property of things that spin, and the more mass that you have on the outskirts, the harder it is to get that up to spinning. If you have a small little sphere like a ball bearing, it's very easy for that bearing to roll down the hill compared to like the rim of a bicycle. You got a lot of mass whooping. And all right, booyah. So yeah, so first moment of a force is this force multiplied by the distance. So even if I take the center right here, there's the force, this is the distance, that's the first moment of this force. Cool. Which is just, in statics, is just going to be called a moment. You know what I mean? It's the first moment of force, though. And it's kind of good to know. Where if it was second moment of force, for whatever reason, we'd be taking that force, the distance, and we'd be squaring that distance. You never square the actual property. This force is the property. It's a distance away. Now we have something. As in second moment of mass or moment of inertia, you have some sort of mass. It's a distance away. The mass is kind of the property, I guess you would call it. And then the distance away is anyway. Moving on. Hell yeah. And that's equal to the product of one of the forces and the perpendicular distance between the lines of actions of the forces. Thus, the first couple right here must have P1, D1, right? The first couple has a moment, T1, and that's going to be the moment, the value of it, which is T1. Also probably representing torque 1. We're calling this a torque as well. And the second couple has a moment T2, which is equal to that force P2 times the distance between those two forces, which is D2. So typical USCS units for moments, let's see, what would be pounds, inches? Pound, inches, hell yeah. Pound, foot, and pound, inches. So hell yeah. So just right there, I just read this, and I didn't want to look at what they were, I just wanted to try to guess for myself. So hell yeah. Pound, foot, and the pound, inch. The SI units for moment is Newton meter. Hell yeah. The moment of a couple may be represented by a vector. The moment of a couple. Hell yeah. So that's what we have this. This is a vector. It has a magnitude and a direction. The direction is axially along this rod, and it has a magnitude. This, is kind of like what that vector is doing. You know what I mean? It's kind of showing, hey, this is how it's twisting. It would be showing the moment of spin if it was a dynamics problem. But a vector is going to be an arrow and a direct an arrow with a magnitude and a direction. The arrow is pointing in a particular direction, and the size of the arrow, it has a size. So there you go. All right, hell yeah. And cool. So a moment may be represented as a vector. And this is good because some things cannot be represented as a vector, especially in material mechanics. Stresses cannot be if you cut this face open and you say that I have pressure or stress because I have a force on the face, like let's say it's just axial, in tension or compression, and I make an arrow out of that, that is a tensor. They do not add like vectors, where this will add like a vector. If I if I have this torque this way with this vector, and then let's say I look top down and I tried to spin it this direction, well, I'm going to have, so this torque is going to be right hand rule. My fingers are sweeping in the direction of this force. So hell yeah, my thumb's going to be pointed that way. Let's say, what am I trying to do? I'm trying to get an arrow maybe that's this direction. No, I want an arrow that's straight up. So if I have an arrow that's straight up, I'm going to have two little welded little nubs, and I'm going to put a force this way. Sweeping my fingers in the direction of that force. My thumb is up, and then I'm going to put a force this way on that nub. And if I had that, if I'm trying to rotate this thing this way and rotate this thing this way, I would have an upward arrow, and let's say those were going to be equal. Well, cool. I can add these like vectors, and that's the same thing as a 45-degree couple going that way. And so, or the arrows would be, this arrow would be this direction, and then and then that would is the same thing. So I'm going to put my thumb in the direction, because if I say that this arrow is this way, let's put my thumb in this direction and then start sweeping my fingers. My fingers sweep around this circle. So let's throw my thumb at this 45, and then my fingers sweep kind of at this oblique rotation, which I would then weld a little rod this way and this way at a 45, and then apply a force in that direction and that direction. So that would do it. So there you go. So hell yeah. So I would come in here, and in this let's say this is the what would we call this? I kind of want to make, yeah, this would be the XZ direction, Z being up, X being this way, and then Y being, no, this would be the Y direction, Z direction, X would be coming out of the page. I wanna put a 45-degree nubbin in the YZ plane, so I would do that, and then I would put a nubbin this direction, and then I would put a force off that nubbin in the X direction, I think. Hell yeah. So 45, and then we'd be applying a force perpendicular to that. Yeah, hell yeah. Yeah, because we would want our thumb to be in this YZ plane in this direction, and then my fingers have to be sweeping that direction. So hell yeah, does that work out? Hell yeah, my fingers sweep still just in the X direction, I think, on that. Whoa, don't quote me on that, but hell yeah, we're kind of just, hey, it brought up the term vector, so we're just going to explore kind of our knowledge of vectors. Hell yeah. Which you might just glance over that and be like, I don't know, vectors, but hell yeah. And it's going to be a double-headed arrow. The arrow is perpendicular to the plane containing the couple. So if here is the plane, if these forces, if I have a little pane of glass and then slide it in here, this arrow is going to be perpendicular to that. So hell yeah. So there you go. The arrow is perpendicular to the plane containing the couple. And therefore, in this case, both arrows are parallel to the axis of the bar, because this plane is the same as that plane. And so these two arrows with the double-headed arrows are in the axis of the bar. The direction or sense of the moment is indicated by the right-hand rule for moment vectors. So yeah, this one we said thumb is towards the fixed end. This is thumb away from the fixed end. Hell yeah. And it says, namely, using your right hand, let your fingers curl in the direction of the moment force. We've talked about that. And then your thumb will point in the direction of your vector. So hell yeah, thumb points this way for this one. Curl the fingers, sweep them up. You can't sweep your fingers backwards. You know what I mean? You're not back slapping this force. You're curling your palm in the direction of this force. And so my thumb's going to be that direction. Hell yeah. And then your thumb will be pointed in the direction of the vector. Man, we're almost through this. An alternative representation of a moment is a curved arrow. So down here is a curved arrow acting in the direction of rotation. Both the curved arrow and vector representations are in common use, and both are used in this book. The choice depends on convenience and personal preference. Moments that produce twisting of a bar, such as the moments T1, these are going to, and T2, these are going to produce twisting. These are called torques, or twisting moments. Cylindrical members that are subject to torques transmit power through rotation. So if you're trying to transmit that moment into something useful, hell yeah, that's going to be called a shaft. But that means that it is moving. You know what I mean? We're applying we're having something move. And that's where, check this out. So let's say this force is a little rocket. This force is a little rocket. And this chunk of mass is yay heavy, and it's floating in outer space. I'm going to light these rockets, and guess what? This chunk of mass is going to start to spin, and spin faster and faster and faster. Cool. Now, and I think these are pretty cool in outer space. Like the one that I'm thinking about right now is well, let's say this, because it seems like isn't that just going to speed up to infinite speed? Well, and how is that similar to a car? How in a car, if I apply a torque to the motor, why am I not why is there some sort of limiting, factor? And it's kind of cool, and I'm glad we brought up the rockets, because rockets are just, mass-changing velocity and impacting. You're basically taking that little droplet of fuel and impacting that larger mass. And you're impacting it as it's rifling through the rocket cone. Very much like a bullet coming out of a rifle. And honestly, in most physics books, they talk about rockets as rifles. Where you have a little bullet, and each little molecule of fuel is a little chunk of mass, and you're taking that little bullet, and it itself, through that chemical reaction of blowing up and igniting, sends itself through the rifling of the rocket. Hell yeah. So one thing we could do, we're going to apply this rocket. It's going to spin. We think it's going to spin and keep spinning faster and faster. But we're going to put a paddle on this little shaft. And then we're going to throw baseballs one at a time. Every rotation, we're going to throw a baseball, and it's going to hit the baseball. Cool. And then so because the baseballs have mass, and in the contact, and then each of the baseballs get knocked, and right at the beginning, Well, I don't know. We're just going to leave it at that. But I think that would be one example where you would have, where this thing would reach equilibrium. As the shaft in a car reaches equilibrium because you have, friction, hills, you're transmitting that torque, and that torque is, and that's the other thing. So torque, moments, still, like from a fundamental perspective, I still consider these forces. And just like, I can even go back to just applying the little chunk of mass floating in outer space. If I apply a force on that, what happens? This mass changes in velocity. Cool. If I have a torque, a moment, a couple, those are just forces. Cool, they're separated by a distance, who cares? But they're forces acting on a mass in a way that, sure, like these are equal and opposite in this direction, and then we have this idea of moment that causes rotation. I mean, it is a huge fundamental, and hopefully it's like, I feel like I'm just like glancing over something, but because you have some of the forces in the cardinal directions, and you have some of the moments. In statics, those are going to all equal 0. If they're not equal to 0, you're going to have motion. In the cardinal directions, you're going to have motion in that, x, y, z direction. If you have the sum of the moments not equal to 0, you're going to have some sort of rotation. But still, even rotation is just mass moving. One thing, especially with torque, is like you can imagine little tiny molecules along this axis. Those don't matter. If I have, and this is where like I want to do a lot of little diagrams of like, hey, if I have one little chunk of mass and I'm going to pin it to the universe. So I'm just going to say that chunk of, that atom is just fixed. And then I'm going to put an atom next to it and there's an electrical connection, whatever. And then I'm going to take that atom and try to, I'm going to take 2 atoms. I'm going to take one atom right here and then 2 atoms on either side. And then I'm going to apply a couple, an upward force and a downward force. Guess what? I applied a force, and I'm going to say that system, I'm going to say that's a rigid body. I don't know, but might have to throw that one away. But I guess the take home is that the center atom cannot resist the other 2 spinning around it. So that's actually one where it's just like the atoms would actually spin around. You could have the center atom fixed. Now, this is a rigid body. That center atom will spin like a wheel. But from that perspective, yeah, so both of those are 2 different analogies, I think. So maybe I messed that up. But the center atoms in this axis, if they just rotate, now I have to ask my brother, but there is just so little, I'm just going to say the motion is negligible. Compared to these 2 atoms on the outside, they actually have to travel around a circular path. They're actually traveling linear distance. The center of those 2 atoms on either side travel linear distances, where the centered one doesn't. So even if you have 3 atoms in a bar and they're just spinning like a propeller, the center atom, hardly, you don't get that Newtonian, it's not going to require any, let's just say it requires no energy to do that. And so that's the deal with torques and couples. You have a force, and sure, the mass chunks out here are going to be traveling. I mean, this whole thing, let's say it was just 0 velocity. We applied this torque couple moment. Now it's going to start spinning. So now this thing has a velocity. We call it angular velocity. But each little point that's like from the axis, like over here, still has a tangential velocity. You know what I mean? It still has, you can still break this thing down in a linear form and see that that torque is causing mass to move and change velocity. Cool. Is that all I wanted to say? That was awful. All right, cylindrical members that are subject to torques. Yep, so that we just covered that. So when we're generating, when we're taking torque in a shaft and getting something else to move. Yeah, oh, that's what it was. Because shafts are applying a torque and wanting movement. And as long as this torque is making mass move, going from zero velocity to some velocity, then you're going to have an equilibrium. So this thing's not just going to keep spinning up. That's why a lot of motors will reach a point where it's just like the torque they're generating will be resisted by the mass that they're moving. Hell yeah. For instance, the drive shaft of an automobile or the propeller shaft of a ship. Most shafts have circular cross-sections, either solid or tubular. In this chapter, we begin by developing formulas for the deformations and stresses. So those two words just make you just want to quit. But hell yeah. So back to the screwdriver. If this screw ain't moving and I apply a torque, this whole shaft twists. I think we visualize that. And that's going to be considered deformation. Even when we had our chunk of metal and we pulled on it axially and I said it lengthened, that's deformation. If I let go, all the molecules go back to the same location. Same thing with torques. You know what I mean? Unless we get to that value where we messed up and when we start bending tools, when we start losing our jobs because we made bridges that fell down, hell yeah. That's when we're no longer in that linear range. So that same thing happens for twisting. You're going to get deformation. You back off the torque. Hopefully all the molecules go back to the original location. That's magic. But if you overdo it and you actually get past that linear range, you get to the yield, the molecules start permanently moving. They can get stronger, cool. But they can move a hell of a lot where your stuff's either tools are bent. Hopefully your bridge is sagging so you can just buy a new one before it falls down. That's the hope. Hell yeah. All right, so in this chapter, we begin by developing the formulas for those deformations. So yeah, that's the one thing I just want to say. It doesn't mean that it got bent. It means that we're applying a torque and things are twisting. So it's just as we have a tank and two people go push on either side of a tank, that tank did change in length. And so that's hugely important to know and understand in material mechanics. That if you can imagine, that's two humans applying a force that you think is microscopic or untangible, but hell no, that is a legitimate, that's classical. There's nothing funky going on with that. That tank literally will change in length. Okay, hell yeah. And then the stress is involved, you know what I mean? The metal if you cut that tank cross-sectionally and you take up all the cross-sectional area of the steel, let's say it's 100 inches squared of steel, and you're applying a force on either side of 100 pounds. Cool. You're going to get 1 psi on that tank. So hell yeah. And you're going to get 1 psi. So if you could generate 1 psi of axial compression in a tank, that number now isn't astronomically small, because that tank will yield if you put 50,000 psi. You know what I mean? So if you got 50,000 people on one side and 50,000 people on the other side, all pushing 100 pounds, and there's 100 pounds of cross-sectional steel on a tank, you could get it to permanently deform. You know what I mean? So there you go. And if two people, or you get it right to the yield. And let's say that tank is 10 meters long. If you have a 1 meter thing of steel, This is a good number to know. For steel, it's going to change by 0.002, or just remember 0.2%. But if I have, and how do we use that number? If I have 1,000, if I have a meter bar of steel, that's going to be 1,000 millimeters. 0.002 times 1,000 is 2 millimeters. So if I have a 1 meter bar of steel, I just think a 1 inch bar of steel, and I push on it, and it generates, steel can withstand 50,000 pounds, and both those are synonymous. 50,000 pounds of pressure pushing in on that 1 meter bar is right at the yield. And that thing will shrink by 2 millimeters. So that 1 meter bar will now be 998 millimeters. Cool. And that's where your steel bar gets permanently deformed. Or right at that point, you could let go, and magically all the molecules go back to the same location. Okay, hell yeah. So, and that's going to be, for a 1 meter bar, that's going to be 2 millimeters. If we have a 10 meter tank, that's going to be 20 millimeters. So the tank can, the literal tank that's 10 meters long, yeah, that's doable, now can, with those 50,000 people on one side, 50,000 people on the other, pushing with 100 pounds each, and there's 100 inches of cross-sectional steel going through that tank, you can get that tank to shorten by 20 millimeters, which is just less than an inch, and that could be visual. That'd be a hell of a lot of people. You wouldn't be able to put that many hands on the tank, but still, you're going from 2 people pushing on a tank and knowing that there is 1/50,000th of an inch. So there you go. So let's say you could, you get a tank that's 24.5 meters long. Cool. You get those 50,000. That tank will yield at 1 inch. You know what I mean? It'll shorten by an inch if the tank is 24.5 meters long. So if you get 2 people on either side of a tank and they're pushing on it with 100 pounds, and you got 100 inches of steel in between that tank, and there's probably way more steel cross-sectionally in a tank, because 100 inches is just 10 by 10. I don't know. A 10 by 10 inch chunk of steel that's stout. Still probably not a tank, but maybe close. Probably not, though. Anyway, if you push on that, those 2 people are only going to be 1/50,000th of an inch. And let's say it's 100,000. Let's say it's you're even worse. You're just 100,000ths of an inch. Well, do we know what 100,000ths of an inch is? No. But let's say you were better and it was 10,000ths of an inch. Hell yeah. If 2 people could actually push twice as much, hell yeah. That tank would shrink by a 10,000th of an inch. And I think we're all familiar with machinists working in thousandths of an inch. And the one that I use for thousandths of an inch is well, it's not a thousandth, but playing cards. Playing cards, 50 of them, or 52, are about a ½ inch. So if you have 2 decks of playing cards, you have about 100 cards, and you have about 1 inch of cards, stack of cards. And so each of those is going to be 100th of an inch. So 1,000th of an inch is if each playing card, which are kind of thick, you know what I mean, if there was 10 sheets pressed together to make that one playing card, one of those sheets would be 1,000th. But now just imagine one playing card out of a deck of cards, and there was 100 thin sheets that made up the thickness of each card. That would be a 10,000th of an inch, and you'd have to have 200 of them to actually, that's the distance that tank is shrinking. But still, that's imaginable. You know what I mean? I can imagine it. I mean, we're still a factor of 10 to 100 to 1,000 from it being realistic, or just like tangible. But there you go. So those are the things that material mechanics does. You apply forces. Forces generate molecules to crunch in, stretch out, twist. And even when we talk about twist, that's why I wanted to dive into torque, torsion, is because, well, I think we're going to end it. But yeah, we have to take a small little. Yeah, it's interesting. You know what I mean? What holds, like on the out. Let's say this is not a solid. This is just a hollow tube of steel that's only one molecule thick, and I'm twisting it. What is making? And now let's say I just have two rings. I have two rings of molecules, a bunch of molecules in a ring, and those two rings are touching each other. So we do have, and that's where I just think covalent bonds, you know what I mean? Friggin' A. Just think covalent bonds and just know that covalent bonds also behave linear elastically. They do move to increase, to resist force. They break right away, but still, when I twist this ring of atoms this way and that ring of atoms that way, what keeps them from not just spinning freely? Because I do like and next time I'll do some drawings, but if I have an atom here and an atom here and an atom here, these two atoms will just spin freely around the center one. Hardly any resistance at all. So this gets into the idea of having at least 4 in a square. So if I have, and then let's do 2. Sorry I don't have my pen, but let's say I have 2 atoms right next to each other. Now this, I could have one fixed. This could just spin around very easily. I could fix this one. This could spin around very easily. But with that, the changes in the deformations are really small. So all I want to do is take 2 atoms that are next to each other, bonded, let's say covalently, and then I want to take, and then this atom is just fixed to outer space, and then I want to move this atom just straight up. Because I have a circle here, and if I just move it just a little bit, straight up is still kind of just in the path of a circle. And we just said it's going to take no force to get that to go in a circle. So technically, it's not going to take any force to just move that slightly up. So keep that in mind. Because moving this one slightly up is where is enough movement for, like, in a material mechanics perspective, for that to fail. I mean, we're talking very small, like the tank. The tank can squish in 1 inch before it fails. The tank can lengthen by 1 inch. A 20-meter tank can lengthen by 1 inch before it fails. That's wild. It's not very stretchy. And then metal is, like I said, you can stretch steel to 30. Well, I didn't say this, but you can stretch steel to 30% because it stretches like taffy. But that's why I think, from a jobs perspective of trying to keep people safe, keep your job safe, keep everyone safe, keep your tools unbent. Think of bonds as being covalent. You know what I mean? Where the second you bent something, well, hell yeah, you did something wrong. You know what I mean? You probably killed something. You know what I mean? If you think of material mechanics like that, then that yield, wild things happen, and you can actually design for parts of things to yield and others to take up the slack. But, I mean, if your climbing carabiner starts to yield, you got issues. You know what I mean? And so there is still that world where it's just like, hey, let's design everything in that linear range. And whatever weirdness happens outside, you know what I mean? Hopefully none of the molecules in our system ever got above that linear range. There's plenty of strength in that linear range. Basically, all the strength happens in that linear range. 99% of that strength, basically. Cool. So 2 atoms right next to each other are not rigid. You know what I mean? So like, and then again, we have to take this and model it. Take a little chunk of square, And then this is just a hollow. We're going to say this is hollow. I'm going to say this whole cylinder is a hollow cylinder that is made up of atoms just on the outside. They're not even 2 atoms thick. So on the skin of this, let's get some more coffee, water, and then we'll finish this video. All right, hell yeah. But you need at least 4 atoms. Two is not going to be. So why is 4 atoms rigid? And you're totally going to have to imagine this. Because 4 atoms, so you have covalent bonds, and I'm sorry, I'm not a chemist, but I'm treating all bonds as if they're just magnetic. Like these are just like high strength magnets. 4 high-strength magnets attached to each other. At any point that if these magnets get far enough away, they're going to separate. But that's not the full model, because also the neutrons and protons, because they're electrically connected with electrons that are very far away, also you can't compress to, well, you could have 2 atoms and you can compress them as much as you want. But when you have a structure and you start compressing, that same thing happens. Is if I have 4 atoms and I'm compressing the top 2, in an ideal situation, the top 2 will just crush into the bottom 2. And you could have an infinite amount of force. But that doesn't exist because the chunks of mass are really far away. And here, they're kind of like, maybe like Bambi's legs, deer on ice. Where if I start to put downward pressure, like, hey, these 2 chunks are just going to roll to the side and then squish in between the other 2. And then you're going to have a failure. So that is kind of what I use for failure in compression. And then obvious failure in tension is just like those 2 molecules get far enough apart, snap-o, you know what I mean? And then think covalent bonds, because they just break instantaneously right at the top of their linear range. So if I have 4 molecules, what the hell happens? Because even when I torque, hey, these 4 molecules, just imagine this cylinder is mondo, like the radius of the Earth, where it's just like, hey, this isn't even, this is flat Earth cylinder. You know what I mean? Whereas just like if I take 4 molecules on, it's literally flat. And so like the curve doesn't even come into it. But still, I'm going to take a little chunk of 4 molecules. One there, one there, one there. This one's going to go up. This one's going to go down because they have to resist this torque. And each of the rings of molecules each have to resist the total magnitude of that torque. But just 4 have to at least, hold back a little bit. Just as if you had an axial piece of steel with tons of atoms on the cross-section, sucked up against and electrically connected to the same amount of cross-sectional atoms just right next to it. That whole system can, let's say if it's 1-inch steel, it can take 50,000 pounds. But let's say you had 50,000 atoms. Well, each of those atoms could take 1 pound. And guess what? You have way more atoms. Avogadro's numbers of atoms. And, well, actually less because thickness of 1 inch of molecules, you would have to have a lot of surface area to even reach the grammage for a mole of steel. But anyway, that aside, each of those molecular interactions between 2 iron molecules provides a certain amount of strength. So this is different, though. We understand 2 molecules being electrically connected together. But if we have 4, what the hell gives? Because we said it's just like if we have 2, this one can just easily move up. This one ain't doing anything. But check it out. If we have 4, and this is kind of the take-home. I'm sorry, I think it would take me 2 seconds to bring up my writing tool. But whatever. I think it's just good also to visualize. So we got the 4 atoms. If I just have these two, this one just easily moves up. This one don't do crap. But let's keep these two stationary, and then this one, well, guess what? It's still like a distance away. So even if I take these two diagonals, well, hell yeah. If I pull this one away from the diagonal, snap-o. If I push it into the diagonal, it can only go the same distance before we get like deer on ice, snap-o. So as I push this molecule up, it's getting closer to that one. So this one and this one are like kind of that deer on ice. Now let's take a look at this one. If these two molecules are moving up, well, compared to this one, these two are going farther away. So however you shear this, 4 molecules, 2 down, 2 up, 2 are going to get farther away, and 2 are going to be closer together. The 2 far away, very, very simple to imagine, like a spring that's going to snap. The 2 closest, maybe deer on ice, you know what I mean? And just think of the electrons, all the mass is in protons and neutrons, which are just astronomically far. Well, maybe not that big of a deal, but they're very far away. At least a magnitude in diameter. I don't know. Is it 1,000? Could you pack? I forget. It's probably at least. I don't know. Yeah, that'd be fascinating. How many protons could you fit in the space? How many protons could you fit in the space of a normal hydrogen atom? I don't know. Is it 1 million? I thought it was a normal number. But anyway. But because those masses are really far away, and you have the electrical connection of electrons, and you push them into each other, there's still you're gonna get slippage. That might be a deformation term. You're gonna fill in voids. Yeah, you're not gonna be linear. So as those two get closer, they can only get close to a certain degree before they just start slipping into different locations, and that is that elastic zone. And the cool thing about steel is, like, if those get the distance that you can pull steel apart is the same that you can crunch it together. That's bizarre. Before you get those deformations, those slippages, those new formations, your bent tools, your broken bridges, you know what I mean, and your losses of jobs. I don't know if people lose jobs. I think they just move on and keep trying their best. All right, hell yeah, such is life. But anyway, so that is the deal with shear. And and I always bring this up because I kind of want to make videos. It's like there is no such thing as shear. You know what I mean? Shear is just definitely down to molecules can't compress together in unstable relationships, and they can't be pulled apart in tension. And especially with materials like chalk, if this was a chunk of chalk, they can't take tension at all. They can take tons of compression. The deer on ice doesn't really matter. But if these two molecules get just a little bit away, that covalent bond, I don't know. See, that's where my chemistry is just totally bunk. But anyway, that's why I visualize covalent, or just at the top of the linear range, they just instantly break. And the tension strength is just very weak in chalk. So as you would shear this up, those two down, this distance increases and you get a break. Hell yeah. And then you get, and the break happens at a 45, and that's going to propagate at a 45 and spiral. You're going to get a spiral fracture. But that is just for things that can't take tension. There's plenty of things, like even steel can take hella tension and is just going to deform. You know what I mean? Well, like I said, you can have a bent tool, and I think that is the brokenness, and that's where it's like, hey, don't bend your tools and stuff like that, because you get plenty of strength. Just get a bigger chunk of steel, make a bigger tool. All right, so we got to end this by saying, yeah, so things like steel can deform. So sure, like, hey, these two can get really far apart. These two can just start spinning, you know what I mean? Where you're not going to get a failure, you're just going to get tons of twists, you know what I mean? And And that's the same thing as pulling on steel and having it lengthen 30% of its original length. That's wild. So same thing with twisting. If it's a steel bar and you twist it, it might just keep twisting. A lot of metal workers do ornamental art. Even without applying heat, you can just start twisting it. It's amazing. So anyway, so hell yeah. So that is torsion introduction. And I'm just glad I wanted to finish with the section that, shear is so misleading and difficult, and it's an awful word. And it's almost, it is literally the reason I failed my first time. And I just didn't go to class. But I was just like, oh man, I missed the first day. The second day, they're way into it. They've already talked about everything. And then you have this word shear, and I couldn't mentally picture it. And even today, it's just, I think it needs to be taught way the hell different. But there you go. That was an introduction to 4 little molecules and how you can shear them. And even though this is a circular thing, those 4 molecules, that's happening all along the, the cross section on the perimeter. It's also happening inside if this is solid. But again, the inside molecules can't take a lot of torque. That's going to be for the next videos. But hell yeah. So we did the introduction to torsion. Booyah. This was torsion. This was material mechanics. I do like this book. Material Mechanics Gear. The Hibbler book is also good. I would get both of them if you're learning material mechanics. Well, hell yeah. Thanks for joining me, and that's a video.